If we can be sentimental for a second, some things in life remind you of simpler times. Maybe it's a well loved book or a familiar place. For us, nothing dials up the nostalgia like the return of a vintage vulnerability. In this episode, we continue our discussion of the Cetus hack. With the DeFi side covered in part 1, we now turn to the central mystery. How did the attacker manage to add a massive amount of liquidity with a single token? Well, there's one bug that will make a big number small. And this one was perfectly placed to turn the key and unlock hundreds of millions of dollars. Integer overflows are back, and they've still got a few tricks to play. This is Not Your Crypto Podcast.
Welcome back. Thank you for following us, sticking with us in this three-parter. This is our first three-parter, actually. We've done a couple of two-parters.
Wow.
Three-parter. Yeah, I know, Michael. Like, we're growing older now. We're
That's
getting
a milestone,
bigger.
yeah.
It is. Like, the subjects are getting heavier and the research is getting deeper, that's for sure. So if you're just joining us and haven't listened to episode 1, I strongly advise you go back and listen to episode 1 because it will give you, obviously, a lot more context on what we're talking about here. Because here we're about to go into deep security law, so to speak. So we're talking about a hack that occurred at the end of May. And values vary from what we've seen on open source intelligence, i.e. basically public sources. But it looks like there was a decentralized exchange on the Sui blockchain known as Cetus that was hacked for roughly 220 to 260 million US dollars. The values change depending on who you're speaking to again. And the reason why it's so woolly to get values is because it had a particular set of features that make it kind of hard to track money in some ways, even though it's an exact science. So basically what Cetus did is it provided these things called liquidity pools where people could go in, and if you needed to get access to one cryptocurrency or two cryptocurrencies, or you wanted to deposit your cryptocurrencies and earn an interest on them, you would do so in these things called liquidity pools, which also enable traders to move money around, do whatever they wanted to do with the token if they spotted a trading opportunity, etc., obviously paying a fee. What we're talking about here is those liquidity pools effectively got hacked and drained. They drained the pool. The attacker was able to spot a vulnerability in one of the code libraries, which we're going to go into much more detail about here. We didn't in the first one, because in the first one, we had to explain the context in which they were even able to leverage this vulnerability and drain all the money over and over, up to 265 times by our last count, when Cetus's incident response team were able to stop them. So yes, it's a doozy of a hack. Its technical execution is relatively impressive. Maybe it's just impressive to me and Michael because we're DeFi newbies, and so we just, maybe if you're a DeFi head, you're like, oh, it was always obvious the whole time. But security people have egos anyway, and they always like to think everything's obvious the whole time. But for us, we were just massively impressed. Obviously not at the theft, at the way it was done, but at the end of the day, it's still, obviously stealing is still wrong, etc. In fact, I was personally impacted by this anyway. So that's kind of a brief recap. Is that a fair enough recap? Do I need to go into any more detail, Michael, without giving away the whole of the first episode? Because we don't want to slow this train down, do we?
Yeah, no, I think that's the right level of detail. You can listen to the first episode. Basically, user interacted with an exchange and was able to, with a DEX, a decentralized exchange, and was able to drain pretty much all the liquidity out of a large number of pools.
Mm-hmm.
And the kind of linchpin of that, their ability to do that, which explained how this is the kind of linchpin of that in the first episode, is the bug that we're gonna talk about.
So for those keen listeners who had their notebooks out and were writing down what the actual kill chain was, you may remember in your notes step 3. And step 3 was after the flash swap was done, which was the first step, after the position creation, which was the second step, in which you then decide you're going to deposit your money into, or your tokens, I need to stop saying money, deposit your tokens into the pool. You actually do the deposit. You actually execute the deposit. And what happened here was they wanted access to a large amount of liquidity. That was the attacker's objective. They wanted all the liquidity in the pool to be able to drain it. So they configured their deposit such that it would ask them for a small amount of token in order to get access to a large amount of liquidity value. How does this happen? as an integer overflow. Okay, so first things first, two words there. Integer is just a way that numbers are represented in code, or actually, yeah, in code in any computing language. So it's just numbers. You can have unsigned integers and you can have signed integers, which is unsigned numbers, and signed numbers, i.e. minus numbers if you need to, or not minus numbers if you don't need to represent them. But basically, you need to tell a computer how to represent this number, and you need to tell it via code. So it's that's done via an integer. You define an integer, you define a size of an integer, which is where this gets interesting. You can have an 8-bit integer, you can have a 64-bit integer, you can have a 128-bit integer, you have a 256-bit integer. These, as you can imagine, when you're counting in binary, can become very large numbers or very small numbers, depending on the level of accuracy you need for whatever your code is actually going to be doing. So what is an overflow? Well, here's where it gets sticky. Effectively, when you're defining your integer, you're basically defining a number of a fixed size beforehand. So this is where assumptions always come in. This is where security people make their money, because assumptions are made about circumstances which you can't possibly predict, but you can guess within a reasonable amount of accuracy due to experience you've had. But someone somewhere always finds an edge case. And so this is what happens here in an integer overflow. You basically define the size of a value in code. And if you get a bigger number than that code can handle, if an input, basically a variable, is supplied that is bigger than the integer that was defined in the code, it should, in a safe language, just error out. It should say that's a big number. I don't even know what the error message would be. Michael, you can maybe pull me up on that, what the actual technical term would be.
Integer overflow, I think, usually, or something.
Yeah, so just say that's an integer overflow.
Depends on the language, I guess.
Yeah.
But yeah, like I find, like with this integer over, like with this stuff, I find it helpful in terms of learning and understanding to like start sometimes by not thinking in binary and thinking in decimal and just having it equivalent concepts. So like,
okay, go on.
Like okay, here we go.
Professor Michael is in the building. Let's go.
Oh no. Previous life version. Okay, so like let's say that I define a okay, computers are finite. They only have a finite amount of storage. So when I want to store a number on them, I'm working with a finite amount, right? So let's say, okay, I'm going to define a 3-digit number, and we're going to use decimal. So let's say my each digit, the equivalent of a bit, is able to store a decimal value. Yeah. So like I'm going to store a 3 decimal number. I'm going to store the number like 100, right? So 100, it fits in my 3 places, my 3 place value, 3 place values.
No, that's correct. That is technically.
We're also going back to like grade 4.
Yeah, I love the fact that you go so far back. I am loving this. Everyone's now just sitting there with their legs crossed, looking at it.
Okay, so what happens if I want to multiply that value, 100? What happens if I want to multiply it by 10? Right?
So obviously you now need to shift it along.
Yeah, so in decimal, the way that you multiply a value by 10 is you take your numbers 100, right? And you can think about it different ways. You can think about it as you like add a 0 on the end. So I now have 1000, right? But there's a problem because that's 4 digits. And I only had 3 digits of space. So practically, like the way you think about multiplying these numbers, if you think 100, like written out left to right, the way you think about it is I shift 100. I take each of those place values and I shift them all 1 to the left. Right. So let's say I didn't have 3 digits of space. Let's say I actually had 4 digits of space. And I wrote the number 100, 0, 1, 0, 0. Then I can do my 10 multiplication, right? Because I take 100, I shift those all 1 space to the left. And now I have 1000, 4 digits. I'm good. If I only had 3 digits of space and I had 100, and I shifted all those to the left, what would happen if I didn't like check and kind of protect myself from this? What would happen is that 1 is gonna fall off the left side. Basically, there's no space for it.
There's no space.
And I'm gonna insert a 0, and then I'm gonna have 0, 0, 0.
And so someone comes along and reads that and goes, okay, 100 times 10 is 0,
100
0,
times
0.
10 is 0. if I'm in like a decimal
Mm-hmm.
3 place value
Yeah.
system kind of thing.
Which is obviously
Um,
incorrect.
so that's called an overflow,
Yeah.
right? So an overflow, I intended it to be a bigger number,
Mm-hmm.
but actually, uh, because I didn't have space, the number wrapped around
Mm-hmm.
and became a small number.
Yeah.
So that same concept applies in binary systems,
Mm-hmm.
except it feels a little bit more confusing because we're dealing with bits
Yeah.
and just ones and zeros instead of our familiar like decimal system. But
Yeah.
same thing in a binary system. Let's say I have like 256 bits of space. That's
Mm-hmm.
common. If I have the binary number like 1 followed by 255 zeros,
Mm-hmm.
and I multiply that value by 2
Yep.
because we're in binary. So multiplying by 2,
Mm-hmm.
I take the number and shift it to the left.
Yep.
But I've filled up all my 256 bits of space.
Mm-hmm.
That 1 is going to fall off the left side if I do it by shifting, what's called bit shifting, which is
Yep.
the way you like multiply by 2 in like a circuit.
Yep.
Or in binary, I guess.
Yeah.
And what I'm same thing. What I'm going to be left with is 256 bits of 0. So I've wrapped around to a low value from a high value. I hope that explanation was right.
No, I mean, it makes perfect sense to me. I can't imagine why anyone else would be confused. Long story short, you can get the wrong answer because boundaries are broken. That's kind of basically what it is, and that's where
there is a maximum number
Yeah.
that's defined by the amount of bits that you're working
Yes,
with.
there you
There's
go.
a maximum number you can have,
There's a
and if
hard
you go over that maximum number, you're going to wrap around to the small number.
Yeah, and
Smallest number.
this is a well-known problem, and as I said earlier, basically you have error states that normally cater for this. You can have checks after the fact that normally cater for this, and indeed this library did here. So we're still focusing on step 3, where you actually configure that you're going to add liquidity, but our keen-eyed attacker in this instance had spotted that there was an integer overflow in one of the libraries, that one of the functions that the app called when it was time to add liquidity. They said, oh, wait, there's an integer overflow in this function, which means, and then they went further down into the code and realized that there was a check for the integer overflow, but they found that the check hadn't been configured correctly. This is where it's going to get very sticky. Ooh. So, okay. Michael, do you want to take a stab? Then I'll take a stab. That's kind of basically. Sure. So yeah, the check was inconfigured correctly. Again, back to what we were saying. Integer overflow, make sure that the integer is of a certain size. So, if it's bigger, then we throw an error. But
yeah, let's talk about the equation first a little bit.
Maybe. Oh, okay, go on.
Because I think it's important. It'll be important to describe the mask that the bug is using.
Yeah, got you. Yeah,
mask. So like. The bug is it's downstream of the add liquidity function. Mm-hmm. So I go to add liquidity. I say I would like to add liquidity, and I would like to add. I give as a parameter the amount of liquidity value I would like to mint. Mm-hmm. Right. So that's that really big number that the attacker supplies.
Yeah.
Okay. Add liquidity. Add this much liquidity, please.
Yeah.
So then there's a chain of function calls that go to execute on this.
Yeah.
And there's one function's called get delta A, I think.
Yeah, it is. That's
right.
Correct.
Which is supposed to calculate the amount of token A, so the amount of one side token of the pool that you would need to add to mint that liquidity value.
Yeah.
So this is like a well-defined formula. This is a well-defined like DeFi DEX kind of formula. And basically what it does, one step of that formula is that it multiplies the liquidity value that you've requested. It multiplies it by 2 to the 64. So 2 to the power of 64. Okay, so again, if we're putting ourselves in thinking in binary, multiplying something by 2, like we just said in our example before, multiplying something by 2 is it's called a leftwise bit shift, or left bit shift left. I don't know, whatever way you say it. Basically, you take all the bits, you move them one place value, one bit to the left.
To the left. Literally like
same way that in base 10 we multiply by 10 by shifting all digits to the left and adding a 0 on the end. In binary, we multiply by 2 that way.
Yep.
So, and then if so, it's not just 2, it's liquidity value times 2 raised to the 64.
Mm-hmm.
So if I want to do that, then I shift it to the left 64 times.
Yep.
Which is kind of a lot of times. That's a lot. That's a big multiplication.
It's a massive
right?
multiplication.
And so it's reasonable that you would need to check whether this is going to overflow, because I forget exactly what is it. This is like an unsigned 256-bit number, I think. Is that right?
It is unsigned.
So like 64 bits of a 256-bit number, that's a significant amount of the place value.
Yes, it is.
So, okay, no problem though. You can check, right? So it's no mystery or no secret what numbers that if you multiply them by 2 to the 64 are going to overflow. You can pre-calculate that.
Yeah.
And then check whether the number you're about to multiply is bigger than that or not. And then if it's bigger, you can say, whoa, hold your horses. Like this, this is going to overflow. Send an error.
Correct.
So that is what they had.
Yeah,
so they had basically like a guard function, it's sometimes called, that would check. It was called check underscore SHLW, which I think SHLW is shift left something.
Wide. I don't want to say word, but
I don't know what the W is.
W.
Anyway, and that function's job was to check if this number would overflow and return an error if it overflowed.
Yeah.
Okay.
And then kill the transaction.
I'll pause there.
Yeah. And so basically, you do the check to kill the transaction dead. That was the whole purpose of this check.
Yeah.
Okay. So,
are we ready to go into the mask bit now?
Yeah, we are. The mask bit is the interesting part as well for me, because
it is.
All right, let's go.
Do you want me to keep going?
Yes, please. You can take the mask.
Gosh. Okay.
Sorry.
Okay. Whew. So, if you think about a 256-bit number, so remember our binary example of it. Sorry, our decimal example of a number that would overflow. Like we said, if we multiplied 100 by 10, it would overflow. Right. So what we could do there is check, okay, are we about to do this operation on a number that's bigger than 100, like 101, and then error out. So that's what they intended to do. So you would intend to check, okay, is this number bigger than 100? That 100, we'll call it the mask. It's not like quite the right technical term, I think. But anyway, we'll call it the mask. If it's bigger than that, if it's 101, that's going to overflow. Don't do it. If it's smaller than that, if it's 99, that won't overflow because you've
got enough place values.
Because like the one smaller number than that has one less place value. So it frees up the place value to shift into. Okay. So the mask that they would need here to check whether a number is going to overflow, it would be all zeros and then a 1 in the 64-bit place, and then all zeros.
Jumping in right here. Yes. Okay. So what people need to understand, if you're not used to counting in binary, and even if you have a cursory knowledge of binaries, it's represented by 1s and 0s in places that are then configured to specific numbers. So as Michael said at the top of the podcast, 0, 1, 2, 4, 8, 16, so forth. And so obviously those bits are either on or off, 1s or 0s. So what he's talking about here when he talks about this mask is effectively you can pre-configure part of the unsigned integer with the mask, saying, okay, you can, I think did they zero it out? No, they didn't. They put all 1s, right?
Yeah, so there's the correct mask, and then there's the mask that they used.
Yeah, and the mask they used was all 1s already, if I remember correctly.
The mask that they used was so the mask that they used was a number anyway, it's a bit confusing because the masks are represented in hexadecimal.
Yeah, so
which is representing the binary.
Yeah.
So I think it's useful to just think in terms of the binary, maybe.
Okay, go on.
So the mask that they used was all 1s from bit position 0 to 64.
Yep.
And then all 0s after that.
Basically.
And then I think it's useful in terms of understanding why that is the wrong mask. It's useful to think about what the right mask would be.
Okay. Yeah.
Maybe. Or we could start with the wrong mask. What do you want to do?
I think we should start with the way that's easiest for us to explain. So that, because if it's easier for us to explain, then it'll be easier for our listeners to
Okay.
understand.
Okay. Maybe I'll start with what the right mask would be.
Cool.
Is that okay?
Go ahead.
Okay. Cool, man. So the right mask would be zeros from bits position 0 to like 63. I'm out of the
Yeah,
I
that's
don't know if I'm
correct.
like off by 1 there.
No, that's correct.
And then a 1
Mhm.
in bit position 64.
Mhm.
Again, I might be off by 1 or something.
Mhm.
Because it's like 0 index, but
Yes.
whatever.
Yeah.
And then zeros all the way after that.
Yeah.
And what that would mean, because remember, 64 is the important like pivot point in this binary number,
Yeah.
because we're going to shift left by 64 bits.
Yeah.
So if you think about that number, 0, 0, 0, 0, 0, 0, blah, 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 1 at the 64 position, and then all zeros after that. That's the smallest possible number that if I shift left by 64, that 1 bit that I've set at the 64 position is going to drop off.
Yeah.
So anything less than that, and all of the first 64 bits are 0, so there's space to shift 64 bits into.
Mhm.
Anything more than that, equal to or more than that,
Mhm.
and that 1 that I've set at the 64-bit position is gonna drop off and overflow.
Yeah.
So that's the correct mask.
Yeah.
All zeros, a 1 at the 64-bit, all zeros after that.
Yeah.
The mask that they actually constructed in the code was not that.
No.
The mask that they constructed in the code was all 1s from 0 to 64,
Mhm.
and then all zeros after that.
Yeah.
So the mental exercise is to think, okay, to understand this is to think, what number could I construct that is smaller than that mask?
Mhm.
Sorry, incorrect. Wait, what number? Yeah.
Yeah. No, you're
What
correct.
number could I construct smaller than that mask
Yeah.
that would still overflow?
Yes, basically.
Because if it's smaller than the mask, it passes their check.
Yeah.
But if it still overflows, then it's still useful to me because I've still got the bug going off.
100%.
So if you think the mask is all 1s in the first 64-bit positions and then all zeros after that,
Mhm.
I can easily, just as like a mental exercise, I can easily construct a number smaller than that that will still overflow. I just take any of the 1s in that 64-bit position, in those first 64 bits.
Yeah.
If I flip it from a 1 to a 0,
Yeah.
then it's smaller
Yep.
because I've reduced the place value there.
Yep.
But it will still overflow because there's still lots of 1s in those first 64 bits
Yeah.
that will drop off to the left. So basically, like, I mean, you can think about it as like a number line. There's a certain value that will overflow.
Mhm.
The mask that they set was not at that value. It was bigger than that value.
Yeah.
And so there was a space in the number line between the value that will overflow and the value that their mask starts catching, where I could silently overflow.
So
I could
effectively,
overflow without being detected.
exactly. So this is the key point here for those who are still trying to follow along, and I respect you and commend you. So effectively, they've set up a check for a specific size, but the size is still bigger. The check that they have is bigger than the size of the integer can handle anyways.
Yep.
So what happens is an attacker notices discrepancy, this difference in expectation and circumstance, and says, okay, I can basically pass the check but still overflow the actual integer that is going to get passed to this add liquidity function, which is then going to still overflow and wrap around and ask for a very tiny amount of tokens. I'm going to repeat that one more time. The check was configured for a number that is bigger than the size of the actual integer itself. So what happened was the attacker noticed this and said, I can supply a number that will pass the check with the mask because of the way they've incorrectly configured the mask, but will still trigger the overflow because, again, the number, the integer, is smaller than the mask check. Trigger the overflow, no error message. The computer will then say, oh, okay, it's now overflowed. The number's dropped off the end. It's now a very, very small number. You only need to give me a small amount of tokens in order for me to mint a large amount of liquidity because the large number's already gone through.
And I think, yeah, so then let's go back to the equation
Mm-hmm.
to kind of put this bug like in context of the equation for the attacker,
Got you.
right? So the equation is this in this get delta A function.
Mm-hmm.
Delta A means like the change in token A that you need to supply
Yep.
to mint the liquidity value.
Yep.
So the formula specifically, we're going to skip over a little bit of detail because it has to do with the position creation.
Mm-hmm.
We'll skip over it a little bit, but we'll still say something about it.
Yep.
When I define that config that defines the position of liquidity I want to add,
Yep.
I give it two values. They're called tick values.
Yep.
There's an upper tick and lower tick.
Yeah, which is basically
In
upper
this
bound and lower
equation,
bound, really, of the
yeah.
range.
So it's not going to be like super important, but it's a little bit important.
Mm-hmm.
But basically, the equation is a division equation.
Mm-hmm.
So there's a numerator and a denominator.
Mm-hmm.
In the numerator, it subtracts the lower bound from the upper bound. So there's like a upper bound minus lower bound,
Mm-hmm.
multiplies that number by the liquidity value that you are looking to add, and then multiplies that by 2 to the 64.
Yep.
So that's the numerator.
Mm-hmm.
So if again, the place that overflow is the liquidity value times the 2 to the 64.
Yeah.
So that isn't, if we were not dealing with overflows, that would be a very large value.
Super large.
But it actually wraps around. If I know the value to supply, I can get it to wrap around to be small.
Yeah.
So then in the numerator, I have a small value times that tick difference times that upper bound minus lower bound. And then I divide, it's a division. So then there's a denominator. I divide that by the tick range multiplied by each other. So the upper bound times the lower bound.
Basically.
So the reason why I end up with like such a drastically small number is not just the overflow. Like if I had just the overflow, I would still end up with a smaller number, but not such an outrageously small number.
Yeah.
It's that the numerator gets small because of the overflow, and the denominator, remains larger because it's this multiplication of the tick values.
Yeah.
And so it's not just that the overflow is wrapping around. It's that I end up with like a small numerator, large denominator division, which basically becomes like the minimum value I can add, sort of thing. So that's why. So this is like this is the entire pivot of the attack chain. Like if it wasn't for this like single bug,
none of this would be possible.
All the DeFi that the attacker did would just be normal, right? Or like he wouldn't be able to do it because he would have to add so much token value that the attacker wouldn't just have.
Exactly.
So, okay.
Wow, you did well there.
Where are we at?
So we're basically at the integer overflow and how it was within his settings, basically how they exploited the integer overflow and why it was necessary for them to actually have understanding of both contexts, i.e. how DeFi works and how liquidity pools work when it comes to minting liquidity value as a representation of the actual tokens in that pool.
Yeah, so that bug is the thing that breaks. Like in the first episode, we talked about the important bit being the integrity of the mapping or pegging or however you want to kind of describe it between the liquidity value that the DEX is keeping track of and the tokens in the pool. And this bug is what breaks that. This overflow is what breaks that, because that's what breaks the integrity of that relationship between those two numbers and what allows the attacker to mint a large liquidity position without providing the token to back it up. The interesting bit, a sidebar interesting bit.
Go ahead.
Is that like these bugs have become rarer, right?
Yes.
Overflow bugs in particular, both integer overflow, its cousin, the buffer overflow,
more famous cousin,
it's much more famous cousin. I'm glad the integer overflow is getting a bit of love here. Yeah. They become much rarer in the past, it's been a while now. It's past 20
I would
years,
say
honestly.
20. I was going to say 20 at the very least.
Yeah. And the reason why is because we started designing programming languages to automatically not be vulnerable to this, more or less. Like they have built-in features that do these kinds of checks correctly and all that kind of thing.
Yeah.
So like the kind of interesting thing here is the move language. That's the right name.
Yeah,
right?
yeah, that's
the
correct.
Move language.
Move language.
most of it actually is designed to be safe
Yeah.
to integer overflows. Most of the functions of it are designed to be safe to integer overflows.
Mm-hmm.
Um, the one thing that is not safe to integer overflows, I think, if like whatever I read about this was right, is this particular bitwise shift left.
Mm-hmm.
It's like the one piece of space there is to do an integer overflow,
Mm-hmm.
or one of a very limited kind of move set to do this integer overflow for the attacker. It's in this shift left function.
Mm-hmm.
Other functions are designed to be safe to overflows.
Yeah.
And I'm sure there's a design reason for that.
Yeah.
Like, that doesn't seem like it's just an oversight or whatever.
Yeah.
It's probably a design reason for it. But that's interesting. That like we talk about how narrow the needle that the attacker is threading here
Yeah.
is. Like, that is extremely narrow, right?
Extremely narrow.
And then not only is it the one place that's vulnerable, but the smart contract designers knew that it was the one place that was vulnerable and tried to design a check for it so that narrowed the needle even more, right?
Yep.
But there was a bug in the check, and that bug gave just the right amount of space for the attacker to maneuver this input, right?
Which is, I mean, it's absolutely crazy. It's absolutely crazy. And again, it's funny how, again, we come back to this thing within crypto where a small bug can be leveraged to a devastating effect, because in crypto, the value is literal dollars and cents, pounds and pence, euros and cents. So what happens is the impact is just magnified, and the velocity at which things move is a lot quicker than anything in Web 2.0. An integer overflow in Web 2.0 would probably give you maybe crash the program. I don't even know what it would be leveraged into.
An integer overflow in Web 2.0, I don't know what it would give you.
It's not very much. I'll tell you that for free.
Like a 500 error.
Yeah, exactly. 500 error on the
Yeah.
server. And if it's a thick client, I don't even know where you're going with that. So at the same time, I still think this was actually a fascinating bug that they exploited. And it's not just seeing the bug, it's being able to understand where you can actually interact with the bug, because they knew at some point they would be asked to supply, they could be asked for a number of liquidity that they are going to supply into the pool. And therefore, they would also then conversely be asked, well, not conversely, they'd subsequently be asked to supply the token as well. So they kind of knew those are the two bits they can control, and they knew how the formula worked, and they exploited it to devastating effect 265 times. I'm going to say that a lot because that's a crazy number in 15 minutes. Obviously, they automated a huge amount of it.
Yeah.
Okay, if you're still with us, not asleep, not with a headache, not angry, or not drastically quickly writing an angry comment saying we explained it wrong, thank you for sticking with us. There is a third and final episode in this series that we will be releasing after this as well, which is where the plot thickens again, because guess what? The attacker didn't get the cash. That's the bit we kind of get behind. So at the last time I checked while doing the research, I think plot twist, 200 million, I think, maybe even a little bit more, is either frozen in specific wallets that everyone is keeping a very keen eye on, or has been reported to the authorities, the necessary authorities. I think FBI is involved as well. So that was an interesting plot twist, because it's a case of, this is all decentralized infrastructure and no centralized parties. How is anyone able to freeze the money? Well, that was a very, very hot button topic within the SUI community, and we have thoughts as well. So we will be talking about why they weren't able to actually steal or take the money out of the ecosystem, and how it got frozen, and whether people actually agreed that it should even be possible for that to happen. Because again, we're kind of harping back to our previous episode on Sonium. Aren't these supposed to be censorship resistant?
I was thinking that too, on governance.
So it's going to be a governance and philosophical one. Stay tuned. We will be back in the next episode with our thoughts and exactly what went down. Thank you for listening so far. See you soon.